Welcome to another new episode. Like always, today we are here with an exciting topic that will boot your knowledge. So, without further ado, let's jump straight into the main discussion.
Welcome to today's Explainer. I am absolutely thrilled about this one today because we are tackling what is, without a doubt, one of the most mind-bending, complex topics in modern science, quantum computing. But don't worry, we aren't going to get bogged down in heavy equations or dense academic jargon. No way. Instead, taking a cue from our source documents, we're going to explore this whole revolutionary technology through a really simple, everyday lens. We're going to treat it like a story about magic building blocks. It sounds a bit crazy, but it's a framework that actually helps even the most advanced researchers visualize the impossible and make sense of rules that just completely defy standard logic. By the time we wrap up today, this whole quantum world is going to feel a lot more tangible to you. Okay, let's dive into this. I want you to just take a second and ask yourself a really simple question. What if a computer could actually do magic? I mean it. I want you to imagine a hero for our story that entirely defies classical physics. This isn't your normal, everyday machine that follows the standard rules of gravity and mechanics that you and I are used to. Instead, this thing operates in a strange, hidden realm down at the subatomic level. Down there, the impossible actually becomes possible, and reality behaves in ways that, well, honestly, almost feel like sorcery. And this magical framing, this is exactly what scientists are dealing with when they try to harness quantum phenomena.
Which brings us nicely to Chapter 1, Meet the Magic Machine.
So our hero here is the quantum computer, and because it taps into these bizarre natural rules, it has some absolute superpowers. It doesn't just crunch data the way your smartphone does, it has the potential to solve incredibly complex puzzles exponentially faster than our old regular computers ever could. I'm talking about a large-scale quantum computer that could easily just shatter the widely used secret encryption schemes that are currently keeping the entire global internet secure. No joke. On top of that, it could give physicists the ultimate tool to perfectly simulate physical reality. We could be designing new life-saving drugs or discovering entirely new materials in days rather than decades. But as with all good origin stories, our hero is still pretty young. Right now, this machine is mostly just practicing its magic on highly specialized tasks in experimental labs. Let's move on to Chapter 2, the special blocks. And this brilliantly illustrates the core difference in how these machines are actually built. To really get the magic, we have to look under the hood. If you think of a normal computer as being built out of plain, boring wooden building blocks, that's our classical bit. It's super restricted. It can only ever be in one of two states, a binary 0 or a 1. It's fully on or it's fully off. There is absolutely no in between. But on the quantum side, we have the qubit. This is our magic block, and it exists in a linear combination of states. So it isn't limited to just being a 0 or a 1. It actually holds a rich, overlapping mix of both at the exact same time. We actually call this magical property quantum superposition. This is literally the primary magic spell of our qubit. Imagine you're flipping a coin. While that coin is spinning rapidly in the air, it isn't strictly heads or tails yet, right? It's just this blur of both possibilities. The qubit exists in this linear combination right up until the exact moment you capture it and measure it. And the second you look at it, the magic collapses. A probabilistic rule forces it to become just one standard state, a 0 or a 1. But while it is spinning there unobserved, it holds this incredible overlapping computational potential.
All right, Chapter 3, Amplifying the Magic Trick.
So just having a bunch of these spinning, magical blocks isn't quite enough on its own to solve massive problems. If you just grab a magic block out of the air, the result you get is going to be completely random. Scientists actually need a highly specific recipe to make this work, which is called a quantum algorithm. Here's how it goes. First, the computer manipulates the qubit in a very careful way. Second, it creates wave interference effects. Think of this kind of like dropping two pebbles into a perfectly still pond. Sometimes those ripples crash into each other and cancel out, and sometimes they perfectly align to make a massive wave. Finally, quantum algorithms use this exact wave interference to amplify the probability of getting the desired result. Basically, they cancel out all the wrong answers and build a huge wave toward the right answer. That way, when we finally measure the block, it gives us exactly what we're looking for. Now, every great story has to have some conflict, right? So what happens if our spinning, hovering magic blocks get bumped? Every superhero has a kryptonite, and it turns out our quantum hero is incredibly, almost frustratingly fragile. And when I say bumped, I mean by literally anything in the physical world. A microscopic change in heat, a rogue magnetic field, or even just random cosmic rays passing through.
That leads us into Chapter 4, the problem with noise.
As researchers are painfully finding out, if a physical qubit isn't kept perfectly safe and totally isolated from its environment, it loses its special powers. The official scientific term for this tragic loss of magic is quantum decoherence. Think of it like trying to build this massive, impossibly delicate tower out of playing cards, but you're doing it in the middle of a very windy room. Every single tiny interaction from the outside world introduces noise or error into the calculations. And here is the craziest part about all this. This magic spell breaks unbelievably fast. The interference from the environment can actually collapse the superposition prematurely in fractions of a single second, completely ruining the calculation. So how do we fix it? Chapter 5, building quiet rooms. So the crucial point here is that to make this magic actually work, governments and scientists are effectively having to build high-tech fortresses. They absolutely must isolate these qubits from that windy room. For example, one method uses superconductors, which isolate an electrical current by totally eliminating electrical resistance to keep the qubit stable. But to pull that off, the system has to be cooled down to absolute zero. That is literally colder than the vacuum of deep space. Another approach scientists use is ion traps. These use incredibly powerful electromagnetic fields to safely suspend a single, solitary atom in a totally artificial vacuum. Both of these are just brilliant, extreme feats of engineering, all designed to give these delicate little qubits the perfect, quiet environment to perform without getting bumped. Finally, let's look at where we go from here in Chapter 6, the future of quantum. So we know what the machine is, we know how the blocks work, and we see the extreme lengths scientists will go to protect them. But where does this all actually lead? You've probably heard terms thrown around in the news like quantum advantage or quantum supremacy. Researchers have indeed claimed they've reached this milestone, meaning their quantum devices can successfully outperform classical computers on specific tasks. And hey, it is a staggering scientific achievement. But we really need to be careful here. Outperforming a normal computer on a highly specific, highly contrived mathematical problem that was specifically designed for a laboratory test, well, that's not the same thing as running Excel faster or perfectly simulating a new chemical. Now, what's really interesting about this slide is the sheer scale of belief in this technology's future. It has sparked an absolute global arms race. $10 billion. That is the massive amount of global government investment poured into quantum computing as of April 2025. Countries all over the map are committing unprecedented resources into this field to help this technology grow up, to build better, colder, quiet rooms, and to eventually turn those highly specialized lab tricks into something that fundamentally changes human capability. But we do have to remain grounded in reality. The source material puts it perfectly, so let's just read this directly. As of 2026, demonstrations are best understood as scientific milestones rather than evidence for near-term deployment. I think that is the essential takeaway here. Our magic machine is growing rapidly. It is incredibly well-funded, and it can do truly mind-blowing things under perfect frozen conditions. But right now, today, it is still a stunning science experiment. It is an amazing milestone of physics, for sure, but it is not a finished commercial product ready to sit on your desk and solve everyday problems. Which leaves us with one final, lingering question to end our story. When will the magic leave the laboratory? We have the magic blocks, we understand the wave interference algorithms needed to amplify their power, and, as we saw, we are spending tens of billions of dollars to build fortresses to protect them from the noise of the outside world. The fundamental science behind all of this is undeniably real, so the question now isn't if these laboratory milestones will turn into everyday reality, it's just when.
How did you like today's discussion? If you have any questions about this topic, don't forget to let me know in the comment. Stay well, stay healthy.